Okay, so for today's activity, we're going to do chapter 28, sections 3 through 5, and we're going to apply those concepts that you have studied very diligently to concept questions 4, 5, 6, 7, and 8, and exercises 7, 9, 11, and 17. So go work on those problems, think about them, and come back for guidance with each one. We're going to start with concept question number 4. So in this case, concept question number 4, we've got a battery that is supplying current to two resistors that are hooked end to end. So we know those are called in series. Okay? But what we're asking about is what is the power dissipated by each resistor if we know R1 is greater than R2. So what is the relationship between power and resistance? Now, there are two ways of writing that. We can say power equals I squared R, or power equals delta V squared over R. Okay. And what's important is to know, well, what about the I or the delta V? Okay, so the question is, what is the same here, I or delta V? And the answer is the current is the same because these are hooked end to end. Whatever current flows through R1 must flow through R2. So the current's the same. So because of that, if the current's the same for 1 and 2, then the power is linearly proportional to the resistance. And so we can just simply say that P1 is greater than P2 because R1 is greater than R2. Apply that same idea, not the exact conclusion, but the same idea to solve the next one, number 5. Okay? So we now have these resistances. We have these two choices for power. So what is the same? Which one should we use? Well, is the current the same? Not necessarily, because these are different resistance. And so we know that the current coming out of the battery must split between the two dependent on their resistance. So current's not the same, but the potential across them is the same. These are all in parallel. The battery connects the tops together, and the bottom is connected together. So the potential difference across R1 is the same as across R2. So delta V is the same, which means our power is inversely proportional to the resistance of the individual resistors. So we say P2 is greater than P1 because R1 is greater than R2. Okay, very good. Let's move on to number 6. Okay, so number 6, we have a series of resistors, and the voltage across each resistor is given, and the resistance is given. We're trying to rank the power dissipated by each one. And so, given that we know the potential and the resistance, we can write P is equal to delta V over R, delta V squared over R. And starting with those units, we'll just say PA is that much. So go through and find PB, PC, and PD. So PB halves the potential, which is squared, so that means there's a quarter drop. Okay, so 1/2 delta V squared is the same thing as 1/4 times the delta V squared. Or better yet, by 1/2 of the square of the quantity 1/2 delta V is the same thing as 1/4 times just delta V squared. All right, and now the resistance doubles. So when I combine those, I end up with 1/8 PA. PC, apply the same ideas. We end up with a 4 delta V squared over a 1/2 R, which is now we get the square and then 1/2, that 1/2 comes to the top, and we end up with an 8 PA. And lastly, PD, we double the potential, so squaring it up top, squaring that 2, and then we double the resistance down below, and so we get an overall factor of just 2. Okay, so again, applying the ideas of power. Okay, let's move on to 7. I really like 7. We have this interesting arrangement of two resistors. Question is, are those two resistors in series or in parallel? What do you think? Okay, so They look like they're in parallel, don't they? Because they are parallel to each other. But is that the electronic definition of in parallel? The answer is no. These are actually in series, and I can see that if I straighten it out. This is the same as that. Current's going to flow through this resistor and then flow through this resistor. There is one wire without any junctions connecting these two resistors together. So it's the same as drawing it like that. And this clearly shows us that they are in series. So these are in series, not in parallel. So remember, parallel is not by geometry. It's whether or not the potentials are the same across them. Series is when they are, whatever current flows through one flows through the other. All right, so let's go to 8 now. Look at 8. So here we have a battery, and we've got a real battery, which can be modeled as a small resistor with an ideal battery, which we say is an EMF. All right, and we have this hooked across an external load, like a washing machine or hair dryer or light bulb. Our question is, what is the terminal velocity or terminal voltage or the voltage across the ends of the battery? We call those the terminals of the battery. Well, we can see that as current flows through this circuit, then there's a voltage drop across this internal resistor, meaning delta V is smaller than the supplied voltage. Okay, so then our question is, well, if the resistance grows, does the current through this resistor grow or decrease? It decreases, because if the resistance grows, that current must flow through that resistor, and so less can flow through it. And so the current goes down. So if R goes up, the current goes down, which means the power dissipated in this resistor goes down, and therefore delta V goes up. Now, to see that a little bit more quantitatively, we can write that delta V is equal to whatever the battery can supply minus whatever drop there is, whatever potential drop there is across that little internal resistance, which is given by Ohm's law, I times R. Okay? V equals IR. And so, if the current drops, this is a smaller number subtracted from this number, so the overall value is bigger or more so closer to the inherent ability of the battery. Okay, very good. Now let's move on to our exercises. Number 7. Okay, so number 7, we have a hair dryer that's rated at 1500 watts, and that's assuming it's plugged into a household circuit, which is 120 volts. And when it is plugged into a household circuit, how much current does it draw? Okay, so P is equal to I delta V, which means I is equal to P divided by delta V. And if we plug in our numbers of 1500 watts for a 120 volt circuit, that gives you 12.5 amps. Now that's actually quite a bit of amps. That's why hair dryers and other heating elements like toasters and things like that are very dangerous. You have to be careful with those because 12.5 amps is a huge amount of current and could kill you easily if it went across your heart. That's why building codes require that you have something called a GFCI outlet near any water source, so in your bathroom or your kitchen. And these have a little button on them, a reset button and a test button. And inside there's a switch. Basically, it detects how much current's flowing in and how much is flowing back out. Because remember, this is a circuit, so current flows from your power source in your house or from the power panel, and it's got to flow back to the power panel. It's got a little detection that says if some is flowing elsewhere, meaning through your body, then it shuts off. And a very small amount, extremely small amount, smaller than what would kill you. And so it's a protection that allows you to do it. Very necessary for things like hair dryers and again like toasters, things that would be around a water source where water can be a good conductor with the minerals that are in it, usually in a household supply. Okay, that's 7. Let's go ahead and do now exercise 9. So 9, we have this battery supplying current to 2 light bulbs, and their powers are given. Okay. Now we need to be careful here. This voltage is given here. We've got 120 volts. We need to be careful here to understand when you pick up an incandescent light bulb, one that's got a glowing filament that gets hot, it's got a power rating on it. So, for example, P1 is a 60-watt light bulb, and P2 is a 100-watt light bulb. Those numbers are numbers saying this is how much it would pull if hooked up to a standard household socket, all by itself. That means it's assuming it's got 120 volts applied to it for that power rating. When these are hooked up like they are here, the power is different than that value. Okay? And it even could be bigger, but if it was, these would fry. That's what the power rating is. Okay? But the point is the power that's listed on a bulb is assuming 120 volts, and therefore is more so telling you what resistance is there. Okay? And so to understand what the resistance is in these, we need to recognize that this number here, which I'm going to call P10 and P20, these are the numbers, the 60 and the 100, that is assuming it's going to be delta V over R. That is assuming a standard household voltage across it alone divided by its resistance. Okay, so this will be R1. All right, which tells us we can find R1 by solving for this. 60, this is 60 volts, this is assumed 120. So R1 ends up being 60 watts, 240 ohms. And R2 is equal to 144 ohms by the same process. Now, R1 and R2, resistance is a property of the device, not what you're doing to it. So it doesn't matter if it's hooked up to 120 volts or 3,000 volts or 2 volts. The resistance is the same. Now that we have found those resistances, now we can find the actual power dissipated by these two. Now the first question is kind of qualitatively, semi-quantitatively, is just, well, which one draws more power, the 60 watt or the 100 watt? Again, you might want to say, well, obviously the 100 watt, it's bigger wattage. But remember, that is the wattage assuming they both have the 120 volts across them. But they don't. There's 120 volts across the pair of them, but that's split between the two. Okay, so in order to find which one's more, we need to recognize how power is related to the resistance of the bulb, and we know that current's the same. So what we can say is that the power dissipated is equal to the current flowing through the bulb squared divided by the resistance of the bulb. And since current is the same, this is the same as this problem up here that we did. And we can say that P1 is, I apologize, this is the same as this one. Where was I? Sorry, the same as this one up here, because the current's the same. And so P1, since the resistance of one is bigger, then P1 is going to be, I'm sorry, I'm doing something wrong here. I got myself mixed up. We have, sorry, yeah, I was looking at a different part of the problem, the second part. We have P1 is equal to I squared R. Sorry, I wrote this wrong. This was not even correct. I was getting the other form mixed up. So we can see that with R1, the current's the same. Since R1 is a bigger resistor, then it dissipates more power. So the 60-watt bulb, again, that's just the definition of its standard, that is actually dissipating more than the 100-watt bulb, because current's the same and the resistance is bigger for that. Okay, now we want to calculate exactly how much power is dissipated. So to do that, we want to use this, we need to find out how big that current is. So to do that, we need to figure out how much current is flowing pushed by this battery, and we can use the loop rule going around this loop. So we can say, okay, I'm going to I'm going to go around this loop. I'm going to gain a delta V. I'm going to lose an I R1 minus I R2 equals 0. And so I is equal to delta V over R1 plus R2. All right. And because of that, I can now find that current, plugging those numbers in, and I'm going to get 0.3125 amps. So now that I have the current, I can actually find the value of the power for each one, multiplying by its effective or individual resistance. And I'll get that P1 that's actually dissipated is going to be 23.4 watts. And P2 is 14.1 watts. And so the calculations agree that the 60-watt bulb is actually dissipating more wattage than the 100-watt bulb in this arrangement because the currents flowing through it are the same. Okay, so that is number 9. Let's check out number 11. Okay, now this one looks pretty complicated, but we can answer it pretty quickly if we're careful to think about how current flows through a system and what brightness means. In this case, all bulbs are identical. So go take a look at it. I'm going to draw it here. You go take a look at it. Okay, so we have these 5 identical light bulbs. Okay, that means the resistances are all the same. Okay, and so when we're trying to figure out how much power or the brightness of this, it's how much power they dissipate. But if the resistances are all the same, that's the same thing as saying either how much voltage is across each one or how much current flows through each one. Okay, by saying P equals I squared over R, if the resistance of them all are the same, then all we care about is which ones are drawing more current. Okay, so thinking about that, so this whole question is more so ranking the currents flowing through each one. Which one of those has more current flowing through it than any other? Okay, the answer is P, because the battery drives the current, it flows, and all of that current must flow through P. It then splits between the others, but all of it must flow through P. So we can immediately say that P is our biggest one. It's the brightest bulb. Okay, now the other ones aren't as clear to see, but we can, if we're careful, we can think about it. Okay, when all that current gets to this point, it has a choice of going through S, through R, or through Q. But if it chooses to go through S or R, it must go through T again. And so that's going to be more resistance. So it's not only got to go through one of these, it's got to go through that again. But if it goes through Q, then that's the only one it has to go through, and so it can get back. So there's less resistance along this path than through either of these two paths, because they both must combine and go through another resistor. So that means Q will have more current because there's less resistance along that path. So that is greater than the others. Okay, so now we just have to figure out how do these compare. Well, by the same reasoning that P is bigger than the rest, T must be bigger than R and S, because whatever flows through R and S, they combine to go through T. So T must be bigger than R and S. So our final decision is, well, what's happening through R and S? Which one has more current flowing through it? So if you are an electron or a series of electrons, and you're making a decision to go through R and S, well, what informs your decision? It's just how resistive is that path. Well, this path requires S to get to here. This path requires R to get through here. But they're the same, which means they're going to have the same amount of current. If 100 electrons get to this point, neglecting those who go this way, well, 50 of them are going to go through here, and 50 of them are going to go through here. So we say that R is equal to S. Now, to help with that, This is an example where redrawing your circuit might help. Noting that those are all resistors, if I redraw my circuit to look like this, okay, and I've got P sitting here, right? And then it splits and goes through Q, and then splits here and goes through R and S, which combine to go through T. If I look at it like that, it's pretty similar to this. But this makes it more clear that P takes it all, and then some of it goes this route, which we can now see that's a bigger resistance than this one because it's got some here and some here. Okay? And so that makes sense that Q is then bigger. Then looking at that, that makes it a little clearer that T must be bigger than these two. And this makes it clear that R and S must be the same. Again, rewriting your diagrams to help clarify the physics is really valuable. Okay, so we've concluded that ranking of brightness, which is in this case, since they have identical resistance, it's a measure of the current flowing through them. So now let's move on to our last problem, 17. Okay, so looking at 17, this is practicing with a real battery. So we have this battery here, real battery, so it's got an internal resistance R and a perfect voltage source, EMF. It's got a terminal terminal voltage connected across the ends. What we're doing is we're connecting it to an ammeter. All right. Now an ammeter is a really cool tool. We have multimeters to play with, and you can turn a knob to make it an ammeter, which measures current. But the thing about an ammeter, any type of measuring thing, you don't want it to change what's happening in the circuit. Okay? So in this case, the resistance of this needs to be really small so that you can measure just what would be going through this resistor. We don't want to add too much resistance. In fact, we don't want to add any. So the resistance of this is 0. A perfect ammeter would have 0 resistance. And real ammeters have crazy small resistances, allowing them to test circuits well. Okay, so if that is our system, our question is, well, what is the internal resistance? And then how much power is dissipated by the battery in this case? Okay, so how do we find the internal resistance of this? We do know that the EMF here, EMF is a 1.5 volts, and we know that the ammeter reads the current, and that's 2.3 amps. So those are to our disposal. So if we're to do this, and if I look at this circuit, doing my loop rule, I can start here, I go through, I gain EMF, I minus any current through that resistor, and I get back. Because this has no resistance, so no voltage drop, I get back to where I started, so that equals 0. Which that means that that resistance is just simply the EMF divided by the current, which gives us a 0.65 ohms, which is a pretty small resistance for this battery. Next question is how much power is dissipated? Well, now that we know the resistance and we know how much current flows through it, power dissipated by the resistor is IR. I'm doing it again. P equals I squared R. Okay. And so with that, I can plug in the current, and I get 3.45 watts. Now what's cool here, as I want to point out, is say, well, how much power was generated by the battery? Well, that's P equals the I times the EMF, or the voltage that it produces. And if you plug in the numbers there, you get 3.45. And in fact, you can show how this is equal to this by using what R is equal to. And so the power delivered by the battery is the same as what the power is using up, because there is nothing else in the circuit to drain it. That ammeter is perfect with no resistance. And that is the end of this class activity.